my name is Uliana Alekseeva. I am from Forschungszentrum Jülich in Germany. And today I'm going to talk about parallelization and optimization of the FLEUR code. And I will show you new possibilities for all-electron density functional theory. In the MaX consortium, our code is the heavy horse. This is the only MaX code which does not use pseudopotential approximation, and it takes into account all electrons, including the core electrons. This gives it the highest possible DFT accuracy, which is why the result of this code can be used as the reference for all other codes. But there is, of course, a price of it to pay. It's much more expensive computationally. For which situation is FLEUR especially suitable? FLEUR is the code to simulate complex magnetic phenomena and phenomena with relativistic effects, spin-orbital coupling, topological effects, and so on. The code underwent significant optimization procedures during the MaX project. First of all, the code was restructured. Huge subroutines doing all possible things at once were split into dedicated modules. This modularization disclosed heavy computational kernels. These kernels were rewritten in such a way that the usage of standard math libraries were possible. This is not only improved performance, but also made the code performance portable. But of course, the performance tuning is an iterative process which you have to repeat again and again as your test cases grow. Now, FLEUR has distributed memory parallelism as well as shared memory parallelism, and the performance inside the code is mostly ensured by the usage of standard optimized libraries. This is a small example of performance tuning, of the result of performance tuning. On this slide, you can see the performance difference between pre-MaX version of the code and the code in the year 2018. The usual run of FLEUR is an iterative process. Computationally, every iteration is the same, so the scaling is measured only for one iteration. The execution time of such an iteration is plotted here against the number of nodes. That means the lower the values are, the better. The magenta line represents the old code, and the other two lines, the new one, pure MPI version together with the hybrid one. The old one was only MPI. As you can see on 16 nodes, for this test case, copper solar was over 200 atoms. The optimized version is more than 4 times faster. But of course, we didn't stop at that point. And soon enough, it became possible to simulate much larger systems. On this slide, you can see 3 systems with over 1,000 atoms. The largest one is the strontium titanate. There is a picture of its unit cell below. And to give you a feeling of what we are dealing with, the system has close to 4,000 atoms. Algorithmically speaking, usual FLEUR run is an iterative process where in every iteration you first set up a dense Hermitian matrix, then find its eigenvectors. The length of these quadratic matrices in this case is about 350,000 elements. It takes about 100 minutes to complete one iteration of 1,000 nodes, and you would need 45 iterations for the convergence. Why would anyone be interested in such a calculation? This one helps to investigate an extended defect. You can see it on the slide. A dislocation in the crystal. It's important in resistive switching, and understanding of the phenomena here can lead to novel memory architectures. But as I said, FLEUR's special area of expertise is magnetism. And here, the ability to simulate large systems open truly new perspectives. One of the recent topics are complex spin structures on the atomic scale. Due to the topological protection, These structures are very stable and can be seen as quasi-particles. They are considered promising for many applications, among others, data processing or neuromorphic computing. So far, they were investigated by a multi-scale approach. DFT calculations were applied to get necessary parameters. Then spin dynamic simulations were performed with these parameters. But now it slowly becomes possible not only to verify this multi-scale model, but to explore how exactly the electronic structure is affected by complex magnetism within these structures. And this is an example. On the left is the system to be simulated, a globule in manganese germanium. The arrows shows the direction of magnetization. Outside the globule, they all show in one direction, up. Inside the globule, they form spirals, such that in the middle, on the central axis of this ellipsoid, the magnetic vectors look down. That means that at the edges of the globule, there is a point with a singularity, where adjacent magnetic momenta look in the opposite directions. These are called Bloch points, and the existence of singularity indicates the inability of a continuum model to describe the real situation at these points. This unit cell has slightly over 1,000 atoms, and it took about 2 million core hours on the SuperMOOC NG in Munich to convert it. Well, you would say that was nice, but it was an exascale. But we have far-reaching plans. I was talking about a single magnetic structure which can occupy hundreds of nodes and use up millions of core hours. But actually, one often needs to study a whole family of similar structures, some kind of high throughput screening. And for that, we have an interface for AIDA. Besides, it's very important and interesting to be able to relax the system, to allow it to evolve in time. And such time dependence would require orders of magnitude more computational effort. So stay tuned. Well, that's a summary of my talk. I presented you all-electron full potential DFT code FLEUR, which is now pretty well optimized and is able to simulate large setups with over 1,000 atoms. And I gave you several examples of what is possible now and what we are aiming for. Thank you very much for your attention.